Welcome back. In this video, we are going to learn about post-hoc test after ANOVA. Now, before that, let us see what ANOVA does. Now, ANOVA analyzes the sample variances. Those samples have been taken from populations, and it can comment whether the population means are equal or not. So, for example, there are three populations with mu1, mu2, and mu3, and these samples have been taken from these populations. Variances have been calculated. And analyzing those variances, it can say whether the means of those populations are equal or not. So, hypothesis becomes mu1 equal to mu2 equal to mu3. That means all the means are equal. And the alternative hypothesis will be at least one of the means is different, right? That means if mu1 is not equal to mu2, but mu2 is equal to mu3, then also null hypothesis fails. Or if mu2 is not equal to mu3, but mu1 is equal to mu2, then also null hypothesis fails. If the null hypothesis fails, that means we reject the null hypothesis, right? Then the question arises that which mean is different from these three means? Now, this part is not answered by ANOVA. So, for this reason, we have to go for some other test after performing ANOVA, right? So, here is a researcher, and on the right hand side, you have ANOVA. So, the researcher asks that, well, then which mean is different? Now, ANOVA says that, sorry, that's beyond my capacity. And that's true. Now, the researcher asks again, then suggest any way out. ANOVA says that you may go for F ratio, but after doing Bonferroni's correction. Now, this is one of the tests that ANOVA suggests. That is why it is telling you may, right? So, there are some other tests also based on the situations. So, we follow ANOVA's suggestion at this moment. Here is our movie dataset, and we were dealing with genre as our categorical variable, right? So, this is categorical variable, and we were dealing with the viewer scores. So, this is continuous, right? Now, in this genre, we have three groups of movies: the romantic movies, sci-fi movies, and comedy movies. I am not going into details of how the ANOVA is, the one-way ANOVA is working. I have already explained these steps in details in my previous video. So, in this video, we were dealing with only the results of one-way ANOVA, right? So, here are the three samples. The sample 1 is sci-fi movies. The viewers are 4 viewers are there, and with the 4 scores. The sample 2 comedy movies, and there are also 4 scores. Sample 3 romantic movies are with the 4 scores. Now, this is the mean of sample 1, that is x1 bar is 90. x2 bar, there is a second sample's mean is this much, 89.25, and the third sample's mean is 78. We have also calculated the grand mean, that is x double bar, as 85.75. Now, after performing the ANOVA, we have got these results. We are dealing with between and within. So, between variance and within variance. So, if we go for between variation, the squared deviation actually, this is actually the variation. So, the sum of the squared deviations between will be 361.5, and you have a degree of freedom as k equal to 2, because you have 3 samples. So, k equal to 3. So, 3 minus 1 becomes 2 as a degree of freedom. Now, if you divide this variation, there's a total squared deviation by this degree of freedom, it will get 180.75 as the variance. Similarly, in case of within, you have got the variation as 224.75, and the DOF is 9. So, you divide this variation with 9, and you will get the variance as 24.97. Now, to get the F statistic, that is the F score, you divide the 180.75, this one, with 24.97, this one, and you will get 7.24. So, these steps I have already explained in my previous video in details. So I am skipping that part. So let us concentrate on the post-hoc test, right? Now after this, you see that if we consult the table 2, DOF between is 2 and DOF within is 9, and our significance level is 0.05, then the table says that the critical value is 4.26. And you can clearly see that our F score is 7.24, which is way beyond 4.26. In this case, we reject the null hypothesis. And if we reject the null hypothesis, then it is sure that at least one of the means is different, right? Now, up to this much, ANOVA stops. Now, we have to find out which mean is actually different from the others, right? So, this is a question. Now, we will learn about contrasts of multiple treatment means. Now, here is a table and along with the sample means over here. Now, before learning contrast, first set up the questions. What question do you have in mind? ANOVA told you that the means are not equal. Now, the question is which mean is different? We have to find out. So, the follow-up question number 1 is mu3 not equal to mu1. So, this is our question. We are not sure whether this is true or false. So, this is our question, that mu3 is not equal to mu1. And the second follow-up question is that mu3 is not equal to mu2. Now, you can see that we are comparing mu3 with both mu1 and mu2, but not in any other way. Why? Because from the sample means, you can see that x1 bar is 90, x2 bar is 89.25, very near to x1 bar, but you can see that x3 bar is a little bit far away from these two, that is 78. So, from these figures, you can have an intuition that mu3 is likely to be different from mu1 and mu2, while mu1 and mu2 are same, right? This is the reason we have the follow-up question 1 and 2 like this. Clear? Now, what we learned from the conversation between the researcher and ANOVA. ANOVA suggested to go for F ratio along with Bonferroni's correction. So, what is F ratio? So, F ratio I equal to sum of squares for contrast I by variance within. Now, this I means how many follow-up questions do you have? That means how many follow-up hypotheses do you have? So, we have 2 questions. So, the I is ranging between 1 and 2. Now, see the denominator first. Variance within. It is available in the ANOVA table. Here you go. The variance within is 24.97. But the numerator is unknown to us. The sum of squares for contrast I. That means we have to know what is contrast. We have to determine the contrast. Then we have to go for sum of those squares for contrasts, right? So what is contrast? Contrast is actually sum of weighted sample means. That means you add x1 bar, x2 bar and x3 bar, but those sample means will be associated with some weights. So, contrast Li, we term the contrast as L. So, the ith contrast, that is Li, will be the summation of j equal to 1 to k, Cj dot xj bar. And if you expand this one, then you will get C1 x1 bar plus C2 x2 bar, like that. So, this k is actually the treatment group count. So, here we have 3 treatments. So, k is 3 here. And the Cj's are actually the coefficients for each treatment j. And this xj bar is the mean score for treatment j, what you have got over here. Now, the question is, how will you determine the values of these Cj's? For that, we have 2 constraints. Constraint number 1, summation of j equal to 1 to k, that means k equal to 3, rj dot cj. If you expand this one, then you will get r1c1 plus r2c2 plus dot 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 up to rkck. And this expansion, this added value should be equal to 0. Now, what is this rj? Rj is actually the size of the sample j. Here, each of the sample sizes is 4. So Rj is actually 4. So if you go for calculation over this data, what you have got over here, you see j equal to 1 to k, that means k equal to 3, Rj Cj, that means R1 C1 plus R2 C2 plus R3 C3 up to this much, and that should be equal to 0. Now R1 is 4, so R1 is 4, R2 is 4, and R3 is 4. Now you take common 4, then you get inside that C1 plus C2 plus C3, and this should be equal to 0. So from here you can see that C1 plus C2 plus C3, this is equal to 0. So you take the values of C1, C2 and C3, but those when added will give you 0. Now we go for constraint 2. Constraint 2 says that absolute values of Cj when added will give you 2. That means if you expand this based on our data, then j equal to 1 to 3, then absolute values of Cj, that means absolute value of C1 plus absolute value of C2 plus absolute value of C3, and these added values will give you 2, right? So what you see, if you go for additions for those coefficients, considering the signs, then you will get 0. And if you only take the magnitudes of those coefficients and add those coefficients, then you will get 2. So these are the two constraints you will have for determining the Cj's here, right? So I can give you one example. See, C1 is 1, C2 is minus 1, and C3 is 0. Now if you add these three, then what will happen? 1 plus minus 1 plus 0 will give you 0. Now if you take the absolute values, so absolute values will be like this: 1 plus minus 1 will be 1 plus 0, it will give you 2. Clear? Now here are the 6 questions or 6 comparisons between the sample means. The first one is the mean of sample 1 is not equal to the mean of sample 2. The second one is mean of sample 1 is not equal to mean of sample 3. Like that, you can have these questions. And you look at the fourth one, mean of sample 1 is not equal to the mean of the means of sample 2 and 3. That means you add these two means, x2 bar and x3 bar, and have the mean by dividing it by 2, and compare that mean whether it is equal to x1 bar or not. So similarly, fifth one and sixth one also be there. So these are the questions you may have, right? So in the previous slide, we have learned that the contrast Li will be looking like this, and in our case, it will be like this, right? Now we go for contrast calculation. Now see the first question, the first comparison. x1 bar is not equal to x2 bar. For that, we have a corresponding Li, or the corresponding contrast. We put C1 as 1 with x1 bar, C2 as minus 1 with x2 bar, and C3 as 0 with x3 bar. Clear? Now the first question is that there are two questions. The first question is that why we are going 0 with x3 bar. In the question, in the comparison here, you see that x3 bar is not involved. For that reason, we are giving 0 weight over here so that x3 bar gets eliminated from the system. Clear? Now the second question, if this 1 and minus 1 is swapped between this x1 bar and x2 bar, that means 1 comes over here and minus 1 goes over here. Will it do any harm? No, absolutely not. Because after this statement, you have to go for x1 bar minus x2 bar. Otherwise, if minus 1 goes with x1 bar, then x1 bar will be a minus and plus x2 bar. And this will give you minus 0.75. So whenever 1 is associated with x1 and minus 1 associated with x2, it will give you 0.75. And if you swap these CJs, then you will have minus 0.75. But this will not create you trouble, because in our F ratio, in the numerator, the LIs will be squared. So whether it comes here as a negative or a positive value, it doesn't matter, because these values will be squared. Clear? So for L2, for this second one, x1 bar and x3 bar, you can clearly see that x2 bar is not involved. So x2 bar has been given 0 as the weight. And here randomly 1 has been given and minus 1 has been given over here. So you can swap it and you will get a 12. Right? Similarly, for the third one, we'll be going like this. And see the fourth one now. The fourth one says that x1 bar is not equal to x2 bar plus x3 bar by 2. That means here all the three sample means are involved. So nobody is getting 0 over here. So you can clearly see that x1 bar, this x1 bar is getting the whole 1 here. And x2 bar and x3 bar, the minus 1 has been distributed equally to both of them. That means minus 0.5 to x2 bar and minus 0.5 to x3 bar from that minus 1. Clear? So if you go for calculating like this, then you will get 6.38. Similarly, you can go for L5 and L6. Now we go for contrast sum of squares. SSI, that is the sum of squares for contrast I, will be Ri. That means this Ri is the sample size, and Li square, and in the lower side you will have summation ofCij's squared, right? For example, see, we go for SS1. Now SS1 is having the Ri as 4 because our sample size is 4. So 4 dot Li we have got here 0.75. So that has been squared. And this is a summation of those coefficients squared. That means we have the first coefficient, that is C1, this one is C2, this one is C3. So C1 squared, that means 1 squared, plus C2 squared, that means minus 1 squared, and C3 squared, that means 0 squared. And you go for this calculation and you will get 1.13. So this is the contrast sum of squares for the corresponding number 1 comparison over here. Similarly, you can go for this SS2 up to SS6. And now we have the table like this. The SS1 is corresponding to 1.13. We have calculated. SS2 is 288 like that. Now, based on our follow-up questions, we have these two corresponding rows. So the follow-up question 1 is mu3 not equal to mu1. So for that, we will be dealing with SS2. And for the follow-up question number 2 is mu3 is not equal to mu2. For this, we will go for SS3, right? Now the null hypothesis for the follow-up question number 1, mu3 is equal to mu1. Because we know that null hypothesis doesn't care about any kind of effect. It always tries to remain in a neutral position, right? So it says that mu3 is equal to mu1. And for the follow-up question number 2, the hypothesis, null hypothesis will be mu3 is equal to mu2. Now, one by one, we have to go for finding out the answers. So for this follow-up question number 1, we have to go for finding out the F ratio and all those stuff. And we will make a decision. After completing the whole decision, then we will start doing with the follow-up question number 2. It is not like that follow-up question number 1 and 2 will run in parallel. You cannot do like that. So let us go one by one. So the F ratio will be like this. The F ratio is for each of those contrasts, we have the F ratio like this. Because you see that the variance within will be 24.97. So in the denominator, you have 24.97. It is fixed. And the changes are going on the numerator side. So we are dealing with SS2 and SS2 is giving you 288. So if you go for 288 by 24.97, you will get 11.53. Now before taking decision, we have to clear about one major point first. So here comes Bonferroni's correction. So what is that? See, the comparison count rises. That means you have more comparisons. You will have more probability of type 1 error, right? So what is type 1 error? Type 1 error is this one. That means the null hypothesis is true, but you reject the null hypothesis. So this error is called type 1 error. You have a long list of comparisons and you want to go for all the comparisons and testing, then you will be in trouble of the high probability of type 1 error, right? For example, say there are k tosses, okay? So k times you are going for the trial of an unbiased coin. You have k tosses and the probability of an unbiased coin is 0.5 for head as well as for tail, right? Now we already know that probability of at least one head is 1 minus p raised to k. Now this p is actually your 0.5. Now if you go for an analogy here, then at least one head can be replaced with at least one type 1 error, and you will have 1 minus p raised to k. Now k here k was a trial, you are tossing the coin, and here the k is a test count, right? And the p here, there is a significance level here, is 0.05. Now you see the trouble. For k equal to 5, that means you go for 5 times tests, right? So 1 minus p raised to k. That means if you put p equal to 0.05 and it is going like this, 1 minus 0.05 raised to 5 and 1 minus over here, then this will give you 0.23. Now you increase the increase the value of k to 10, right? So from 5 it is going to 10. Now this value becomes 10 now, and you will get 0.4, right? You increase further, say from 10 it goes to 25. So here this will be 25, and you will get 0.72. That means you can clearly see that the probability of at least one type 1 error is going higher and higher and higher as long as you are increasing the value of k, that means the number of tests. So from here, one thing you are suggested that you apply your intuition and try to minimize the number of comparisons, right? So this is our equation for Bonferroni's correction based on this simple probability theory, right? So this alpha is already known to us. There is an overall hypothesis test. There is a significance level for overall hypothesis test. The overall hypothesis test is significance level for overall hypothesis test is 0.05. Now here is another term, that error rate family-wise. So this kind of error is also called the significance level. The probability of the significance level, that is alpha, is also called error rate family-wise. And here we go with the alpha dashed, and the alpha dashed is new significance level for individual contrast test. That means you have 2 follow-up tests. So the alpha dashed will be the significance level for each of those follow-up tests, okay? For each of those follow-up tests. So overall overall significance level is 0.05. But when our follow-up test is, the count of follow-up tests is 2, we have 2 questions. So 2 follow-up tests. So the number of tests goes high. In that case, if we stick to this 0.05, then we will have a higher probability of type 1 error. So we have to adjust this alpha to some new significance level, that is alpha dashed. Clear? Now the C is your contrast count. That means how many contrasts do you have? That means how many follow-up tests do you have? So we have C equal to 2. So for each follow-up hypothesis test, we will have the alpha dashed as our significance level. Not the alpha, but the alpha dashed due to this. So if you rearrange this thing, then you will get alpha dashed equal to 1 minus alpha raised to 1 by C. Just readjust this side and algebraically, and you will get this. You can have an approximation, not exact equivalent, but an approximation like this, that you have the overall alpha and you divide that alpha with the contrast count. That means how many tests do you have? Just divide that alpha and you will get approximate alpha tests. So in our case, it will be looking like this. We have the significance level for each test as, see, this is the overall alpha, that is 0.05. It is divided by 2 and you get the significance level for each alpha as 0.025. So based on this 0.025, you can decide whether the null hypothesis will be rejected or not to be rejected. Clear? So we have this, the significance level for each test is 0.025, and we have got the F ratio as this one, because we are dealing with the follow-up test, follow-up question, the first follow-up question. After completing the whole business with the follow-up question first, then we will go for the second follow-up question, right? So we avail one online calculator. There are lots and lots of online calculators available for this kind of calculation. Now the variance between, in case of this degree of freedom, you put 1 over here whenever you are going for 2 follow-up tests, and the degree of freedom in the denominator for that, this will be this one, because you are not touching the lower side. This is actually fixed. So variance within is there as 24.97. You are using that. So for that, degree of freedom is 9 will be there as it is. But here on the upper side, we are having 2 follow-up tests. So 2 minus 1 gives you 1. So in this box, we have given 1, but in this box, we have given 9 as it was before. Clear? Now the F statistic, we have provided 11.53. What we have got over here, this one, 11.53, that is the F ratio. And this probability, that is beyond this F 11.53, is 0.008. So this is the probability we are getting from this calculator, right? So the probability of F greater than 11.53 will be 0.008, which is less than 0.025. So we reject the null hypothesis. So it means that mu3 is not equal to mu1. Now we have to go for another test, that is mu3 is not equal to mu2, and for that I keep the job for you. So what you have learned? You have learned contrast, comparisons, how the overall significance level actually is affected due to increase in number of comparisons, and also you have learned how to correct it using Bonferroni's correction. So if you have any question, you can write me in the comment box. In the next video, we are going for two-way ANOVA.